Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video illustrates basic use of deep learning models on DF Robot RDK X3 single board computer using scripts adapted from the D Robotics repositories. The D Robotics RDK suite comprises the X3 and X5 family of products. This presentation is limited to the RDK X3, which is a single board computer from DF Robot for prototyping robots and evaluating ROS2 solutions. The common name for this model is Sunrise. Its logon credentials use the same names. Security experts, please do not get horrified by this common practice. You can always change the password as you must after the first logon to the board. This slide illustrates the key interfaces of the board. These interfaces are numbered in anti-clockwise sequence in the image, beginning with 1 for the USB Type-C power interface, 2 for the MIPI CSI camera interface, 3 for the debug serial port, 4 for a micro USB 2.0 interface, 5 for the USB 2.0 type interfaces, there are 2, 6 for the USB 3.0 type A interface, 7 for the gigabit Ethernet port, 8 for the 40-pin interface, 9 for the HDMI interface, 10 for the power and status LED indicators, 11 for the Wi-Fi antenna interface, and 12 for the micro SD card interface, which is on the reverse side. The board has a 40-pin header interface similar to that used in Raspberry Pi computers. These pins permit interface with input-output signals using a 3.3 volt logic level design. The pin diagram is shown on the slide. More detailed information on this interface is available in the 40-pin function usage document. Download the operating system image for the RDK X3 board from the D Robotics website. The URL is shown on the slide: archive.d-robotics.cc/download/os_images. Drill down from this page to select the release and type of image, desktop or server. Since your first board will be used primarily for evaluation and development work, you may want to select the desktop version. Note that there is a checksum file that should be downloaded too to validate the integrity of the image you have downloaded. This step is strongly recommended. Flash the image to a micro SD card. While there are many ways to flash the image, I used the Raspberry Pi imager for this purpose. After flashing the card, insert it into the slot on the board. Connect the peripherals, keyboard, mouse, display monitor, and Ethernet connection. Then power the board. Monitor the status LEDs. After the boot process is complete, the monitor should display a recognizable background screen. The user account for logon is Sunrise. The default password for this account is also Sunrise. Remember, there are two versions of the OS, desktop and server. For those familiar with Ubuntu, will understand the differences. For others, I am simply going with the desktop version even though the RAM is only 4 gigabytes, which is small by today's standards. The URL to download the image for the RDK X3 is shown in the address field here. So if we go ahead and select that, we will drop down to a folder where the various versions of the images are kept. At the moment, there is only one, 3.0.0, and so we'll select that, and then we can select the release version, which is what we want. Now notice that there is a desktop version and a server version. So we're going to go ahead and download the desktop version. And also, I would strongly recommend that we download the MD5 checksum too. So let's go ahead and click that. So while these files are downloading, and we'll move them over to a folder and then validate it before burning an image on the SD card. Now that we have moved the files to a subfolder, let us go ahead and perform a validation. As you can see, the file has the extension .xz. This format can be easily used by any imaging software, but for the purposes of validating the checksum, we'll have to uncompress it. So here's the command to uncompress it, unz, and it will take a few seconds to do that. It's a 2 gig file, so just bear with me while it does it in real time. And then once that's done, we'll go ahead and get the checksum estimated. So in a minute, shouldn't take too long, and we'll get a file without the .xz extension. So it does it in place and replaces the original file. So beware that it's not going to create a copy of the image file. It's going to replace it without the .xz after expanding it. So it's done, and if I go ahead and now show you the directory contents, you can see the .xz has gone. And so we'll go and do the checksum on that, which is MD5 and without the image. And again, it'll take a few seconds to perform the checksum through the file. And once that's done, it'll echo the checksum and the file name. And then we'll go ahead and print the checksum that was given to us by DF Robot. So that'll be a validation. And of course, there are many scripts available in public domain that'll do a much slicker job, but I just wanted to show you the bare bones here. And you can see that the checksum is that value, and the value given to us by DF Robot is this, and they're identical. You could do a comparison, you could run a shell script, or you can go and download something, and if you have a long list of images that you want to perform a checksum, it's better to go ahead and use a slick script. Let's go ahead and flash the image that we've just downloaded onto an SD card. You can choose your own preferred imaging software. I stick with Raspberry Pi. So obviously, we're not choosing a Raspberry Pi, so I said no filter. Now, when it says choose OS, we're going to use a custom option there and then navigate to the folder where we have the image, and it selects it. And then we have to select a storage device, of course, naturally, where we want to write it. And then we're not going to change any options, customize or anything, and just click on next, and away it'll go. That's all there is to it. Insert the SD card to the bottom of the board in the appropriate slot. Then connect all the peripherals first before connecting the power. Once the power has been connected, the system will start to boot. Check the status lights. Once you get a steady green, then you know that the system has booted up, and the screen should look similar to that shown on the slide. After the system has booted up for the first time, the first step is to establish network connectivity. After the boot is complete, the first essential task is to ensure internet connectivity through Wi-Fi or Ethernet interfaces. If the board is not enclosed in a metallic case, then an external Wi-Fi antenna will not be required. Use the ifconfig command to establish the availability of the interfaces. The board is configured at the factory with a manual setting for the Ethernet IPv4 addresses. Personally, I prefer to use the DHCP server in the LAN to automatically assign an IP address. IPv6 is also available. The utility to connect to the Wi-Fi network is documented clearly. If you have the SSID and password, irrespective of the method you choose, the configuration is simple and does not require a reboot. Changing over to the assignment of IP addresses using a DHCP server requires disabling the manual checkbox and explicitly setting DHCP for the IP address assignment. Naturally, since the board is already configured with a static IP address, you will have to reboot the board to ensure that the DHCP assignment is active. Drop a comment if you have issues on this topic. Once the Wi-Fi and Ethernet connections are operational, you should use a VNC viewer on your desktop to connect to the board. Similarly, use SSH. Remember, the address will have changed if DHCP is enabled for the command line access. Finally, depending on your environment, it is always good practice to change the logon credential. Using the ifconfig command to review your revised network connectivity information. The simplest way to perform network connectivity is to use the toolbar from the main menu, and you can go ahead and configure both the Ethernet as well as the Wi-Fi connections. And you can select edit connections, and obviously you need to have your SSID and password handy. If you want to stay with the manual setting of the IP address for Ethernet, it's up to you. In my case, as I mentioned in the slides, I use DHCP. The RDK X3 software has pre-built examples to help you to jumpstart your evaluation of the board. These examples are under the /app folder. Owing to the need to keep the duration of a video tutorial bearable from a viewer perspective, I will limit myself to the Python demonstrations. I have tweaked several examples in other subfolders that are enumerated on the slide, but let us focus on the Python scripts only, please. There is another subfolder called Model where the deep learning models are retained. The 40-pin samples will permit you to evaluate your Raspberry Pi examples with the RDK X3 with very little incremental effort. The camera demonstrations prefer the MIPI CSI camera interface, but they work equally well with the USB cameras. Naturally, D-Robotics has installed OpenCV and ROS2 packages to jumpstart our learning and evaluation processes. The starter examples are saved in a file called app. So let's go ahead and look at it. And if you can browse here through the file system, you'll see that there is an app folder. And if we select the app folder, you'll see the bunch of samples in here. What we focus primarily on is the Python demonstrations in this folder. So I'm going through some of these, not the YOLO, because the YOLOs are obsolete. I'm going to do a demonstration on YOLO 11 for you. And obviously the models are also important. So there's the folder called basic model, and all 35 models are in here. Again, we will not use these YOLO models. We will download the latest at runtime for the YOLO models. The model files are in the subfolder /app/model/basic. While these model files are intended for use with the starter samples, you can leverage them for your own code too. There are 35 model files. I hope that these can help you to steer your deep learning exercises in your preferred areas of interest. The YOLO pre-trained models can be downloaded at runtime if they are not present in the working folder. Of course, the key prerequisite is that the Ultralytics package has been installed. Some of the deep learning Python scripts provided by D-Robotics are listed on the slide. Efficient NAS-net _M, Efficient Net Lite 4, GoogleNet is also known as Inception v1, MobileNet v1, ResNet 18, VarcoConf.net. Before we dive into running the evaluations with select models, let us take a quick look at the process workflow to prepare a working model. We prepare a dataset by cleaning, pre-processing, and splitting into 3 subsets: training, testing, and validation. For training, we choose a suitable deep learning architecture and use hyperparameters such as epochs and batch size in connection with the testing data subset to prepare a model for evaluation. Using a final unbiased evaluation of the model with data that is not part of the training or testing subsets, the quality of the data significantly impacts the performance of the model. Careful tuning of hyperparameters can improve model performance. Overfitting may occur when the model performs well during training but not on validation. Ensure that the model is fair and unbiased. It should be free from societal biases to the extent practical. This is why data engineering, the least glamorous part of deep learning cycle, is so important. Efficient NASNet is a powerful convolutional neural network architecture known for its high accuracy and efficiency. It achieves high accuracy on image classification benchmarks. Being built upon NAS architecture, it has better performance, leading to improved efficiency and accuracy. It is suitable for deployment on devices with limited computational resources. Our first demonstration is using efficient NAS net underbar M as the model. So let's go ahead and load it. And I really haven't changed anything in the original code except for allowing it to pass parameters through the command line. So as you can see here, we have those little parameters, one for the image file and the other for the model name. So I'm going to go ahead and look at the test runtime parameters for that. And I'm choosing deliberately something different from Zebra underbar CLS. So I'm choosing this file called gulfbirds.jpg. And let me show you what gulfbirds.jpg looks like. And it's important to understand that efficient NASNet is very good at doing segmentation. So it's going to go ahead and do a lot more than just classify the image. And here we have Gulf birds, if I can just pull it up. And you can see it's a lot of wings in here, and that's what we're after. So let's go ahead and run this. And it shouldn't take too long to run it. And in the output, we'll see immediately confirmation that it did see a bunch of wings. And that's essentially to illustrate the time requirements for you to give an idea for a single image on the RDK X3, how long it took for efficient net. So it's good for small devices, and it's very good for segmentation, not just overall classification of the image. Efficient Light 4 models are a family of lightweight convolutional neural networks designed for efficient inference on resource-constrained devices. The small model size makes it ideal for mobile and embedded devices where limited processing power can degrade performance of other models. Applications that require low latency and high throughput, such as real-time object detection for autonomous vehicles or video surveillance. Efficient Light 4 models offer a compelling balance between accuracy and efficiency, making them well suited for a wide range of deep learning applications where resource constraints are a major concern. Let us now look at an EfficientNet Light 4 model. So for that, I'm going to use this other file that I have here. It's basically an Raspberry Pi 5 case. And let's see what this model will do with that image. So let me launch that, and just to show you that I am indeed feeding that file name in there. So let's get out of that and run it. And obviously it does run, and it comes up with a very high confidence, say almost 88%, but it identifies it as a speedboat. Obviously, again, the testing and the training was done with an image that looked like a speedboat, and they probably never thought about using a Raspberry Pi case as a test case. So yeah, just illustrates the fact that you have to be careful when you are doing some validation of your models. GoogleNet, also known as Inception V1, was a groundbreaking convolutional neural network architecture that significantly impacted deep learning. GoogleNet achieved state-of-the-art image classification accuracy on the ImageNet dataset when it was introduced, surpassing previous architectures. The core innovation lies in the inception modules. These modules efficiently extract features at different scales by using a combination of 1 by 1, 3 by 3, and 5 by 5 convolutions in parallel. This allows the network to capture a wider range of information. The multi-scale approach of inception modules helps the network effectively handle variations in object sizes and scales within images. The architecture can be more complex to understand and implement compared to simpler convolutional neural networks. While more recent architectures may offer slight improvements in certain areas, GoogleNet remains a foundational model with a strong impact on the field of deep learning. Let's take a look at the GoogleNet demonstration. The original example supplied by DF-Robot used this image for validation. I'd like to use a slightly different image of the zebra for the validation. So just so that you know that I'm not running the standard image that is supplied by DF-Robot. So let's drill down and pick up GoogleNet in here. And we have GoogleNet in here, exactly the same code. They made some minor variations in allowing you to pass parameters, which are the image file name, as well as the other name at runtime. So it's your call, if you want to use it in that manner. And we can go ahead and look at the configuration setting in here that is not smoke and mirrors. And so if we open up the test file, you can see I've replaced zebra underbar CLS with zebra.jpg, which is the file that I'm using. Let's go ahead and run it. And it shouldn't take too long to run this. And you can see it comes back with the classification of zebra and a pretty high confidence score. So essentially, GoogleNet has its advantages because of the large model and popular, but from a resource perspective, perhaps some of the other models for the robot, DF-Robot RDK X3 board may be slightly different. MobileNet models are designed with efficiency in mind, requiring significantly fewer computations compared to larger models like ResNet or Inception. They have a much smaller model size, making them ideal for deployment on resource-constrained devices like smartphones, embedded systems, and IoT devices. Due to their reduced computational complexity, MobileNets perform inference much faster, enabling real-time applications. Despite their compact size, MobileNets achieve surprisingly good accuracy, often compared to larger models, especially when considering their efficiency. MobileNets can be adapted for various computer vision tasks, including image classification, object detection, and semantic segmentation. Let us examine MobileNet now. And for this, I will use another file that is different from ever been validated. So it's a bunch of pelicans. And again, in the interest of veracity, just show you that I'm feeding in pelicans in here. And let's go ahead and run this and see what we get as output. And sure enough, it does classify with almost 97 confidence that it is indeed pelican. So MobileNet has proven to be very popular because of its lightweight coupled with good accuracy. ResNet is a popular convolutional neural network architecture known for its effectiveness in overcoming challenges in deep neural networks. The 18 refers to the smallest variant of the model with 18 layers. There are ResNet 50 and ResNet 101 models too, with 50 and 101 layers respectively. ResNet 18 achieves respectable accuracy on various image classification benchmarks. It is very helpful in leveraging larger pre-trained models to prepare for platforms with lower computational resources using the process known as transfer learning. It is very popular in real image processing, such as surveillance. I would like to show you now ResNet 18. 18 stands for the number of layers, as we've said, and there's ResNet 50 and ResNet 101, but 18 is the best we can use for the small embedded devices. So let's go ahead and proceed with that. For that, I have a different image now of a cow, and we'll feed this in as part of the settings. So in here, in the runtime parameters, we're telling it to use the cow image, and let's go ahead and run it. And when we run it, you can see that it gives us two classes. One is an ox cart and the other one is an ox. And I hope you can relate to the fact that they probably didn't use images from India to validate their model, so they just relied. And this is how we get societal bias in the data, which I'm warning you about when we do all these deep learning exercises. So here's a classic example of that: an ox cart and ox instead of a cow. Variable convolutional neural networks offer some unique advantages. Flexibility. VargoConfNet can dynamically adjust the size and shape of their convolutional filters during training. This permits more effective training of diverse and complex data. It can handle variations in object size, scale, and orientation within images, leading to improved robustness, improved performance. In some cases, VargoConfNet can achieve comparable or even better performance than traditional models with fewer parameters, making them more data efficient. Designing and training VargoConfNet can be more complex than traditional models owing to the added flexibility. VargoConfNet has shown promising results in various domains, particularly medical image analysis, where handling variations in image quality and anatomical structures is crucial. The final demonstration for the basic deep learning models is the VargoConfNet. So I have the file in here, and let's try and use another completely different file in here. So I have something called Bison that I'd like to run and see if it recognizes it. Okay, so this is the Bison file, and in VargoConfNet, I'm going to go ahead and ensure that I'm specifying. So I have Bison specified, and if we can go ahead and now run it and see what we get as output. And sure enough, it says with full confidence that it is classified as a Bison. So good model experience with VargoConfNet. Fully convolutional one-stage object detection, FCOS, is a significant advancement in the field of object detection in deep learning. Unlike traditional object detection methods that rely on predefined anchor boxes, FCOS is anchor-free. This means it doesn't use any predefined boxes to predict object locations. It operates in a fully convolutional manner, treating object detection as a per pixel prediction problem. Instead of predicting offsets for anchor boxes, FCOST directly predicts the distance of each pixel to the four boundaries, left, top, right, bottom, of the bounding box that encloses the object. Eliminating anchor boxes simplifies the model architecture and reduces hyperparameters. It is flexible in easily adapting to objects of various sizes and shapes. It has shown improved performance compared to anchor-based methods on various benchmarks. The RDK board supports OpenCV, of course, since it's running under Ubuntu. The key thing in OpenCV is when you're doing a video capture, the video index is for some reason number 8. I mean, there's a good reason for it, of course, but I haven't dug into it. So watch out for that. You have to use an index of 8, not 0 or 1 that we're traditionally accustomed to. And then you just use your normal functions for OpenCV. Of course, here's the code snippet that I have for reading in a stream, a video stream. And then traditionally, you can do an IAM-write or an IAM-show. As promised earlier, I'm going to show you just a little bit of YOLO 11 here, because that's the latest and greatest. So I've already done a tutorial on YOLO 11 on the Raspberry Pi. I don't want to go through the whole cycle again. Just quickly want to show you that YOLO works on this board too. We're going to go ahead and let YOLO import the model file, the pre-trained model file, instead of installing it ourselves. And then I have a test image that I want to run with it. So let's go ahead and run this, and then we'll see what happens. So we have test YOLO 11 to be run. And as we launch it, you can see that it's going to take a while to download the pre-trained image. And once that's done, then the model will be classified. I have deliberately chosen a model where there'll be multiple objects. And as you can see now on the screen, it's downloading the model file, which is the YOLO 11N for Nano pre-trained model. Once it's done that, it doesn't take any time for it. So one person and one train. Let me show you the image file that we had fed it. So go back to images here. And from Houston, was it? Yep. So this was the image we fed in. So it detected the tram. I called it a train. And there's a person here, and it detected that person. So kind of works on the RDK here. And obviously, you know, there are lots and lots of tutorials and examples from Ultralytics. And it's my feeling that perhaps this board will be very good for YOLO 11 exercises too. Time permitting, the RDK X3 board will be put through its paces with some basic topics on C++ development, robotics application development with starter exercises in ROS2, line following algorithm, and autonomous mobile robot. We'll also take a look at multimedia development. If you have a key topic or two on the RDK X3 that you are interested in, please drop a line in the comment box. This short tutorial demonstrated Python starter exercises on deep learning models, YOLO 11, USB webcam. The DF Robot RDK X3 board has many features. It is impossible to cover all features in a single presentation. I only wish that it had more RAM, at least 8 gigabytes, and an M.2 interface or two for an SSD and an AI card. But then DF Robot must have good reasons for freezing the design of the RDK X3 with these current specs. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance using free open source software, FOSS, from Ultralytics for YOLO 11 and their excellent community forum for support. And for the backbone of the preparation of this tutorial, from Inkscape, OBS Studio, Kdenlive, LibreOffice, and of course Ubuntu. Also, D-Robotics provided the starter examples. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.